Hello guys, welcome to this video. Today I will give you a basic introduction to pTx at ultra-high field. You may have heard of pTx, but what does it stand for? How does it work? Why do we need it for ultra-high field? I hope after this video you will be able to answer all of these questions. Let's get started. First, I want to introduce to you the ultra-high field. During the development of MRI, it seems that the B0 field keeps getting higher and higher, from 1.5T to 3T to 70 and even higher, which is understandable since higher B0 gives us higher SNR. Normally, we refer to B0 field of 70 and higher as the ultra-high field. Compared to lower fields such as 3T, at 70, the higher SNR can be treated for higher resolution, which is critical for imaging small regions such as hippocampus, as demonstrated by this T2 TSE image. With diffusion MRI, we can see better delineation of the fiber bundles at 70 compared to 3T. Another example of the 70 advantage is the SWI, which further benefits from the increased susceptibility effect. From this figure, you can see that more veins can be seen with better contrast at 70. The last figure I show here is the top image. With 70, the background tissue signal is better suppressed and the arteries are more visible. With the advantages of ultra-high field, naturally we want to increase our field strength, but we cannot just directly jump to ultra-high field. Aside from the engineering challenges, one side effect of ultra-high field is the shorter wavelength of the RF. Intrinsically, the RF is an electromagnetic wave. The wavelength is inversely proportional to the B0 field, which means that at 3T, the wavelength is about 26 cm, while at 70, it's only about 11 cm. This can be problematic. The transmitted RF forms a standing wave inside the scanned object, for example, a human brain, and 11 cm is less than half of the diameter of the human brain, and that will lead to significantly inhomogeneous distribution of the B1 field. Naturally, people came up with this idea. What if we use multiple transmit channels and let their standing waves even out? And since then, we entered the era of the pTx. pTx stands for parallel RF transmission. This slide shows the difference between the conventional 1Tx and the pTx. 1Tx uses a circular polarized coil, while pTx uses multiple transmit channels that are driven by separate sources. By manipulating the relative amplitude and phase of each channel, we can obtain a relatively uniform B1 plus field. As shown in this figure here, one subject was scanned with a T2 weighted sequence at 70, with 1Tx and pTx back to back. Apparently, with 1Tx, the B1 field inhomogeneity led to signal loss at temporal lobes, while with pTx, the signal intensity was relatively homogeneous. However, this is just one very simple example of how pTx helps. There is so much more it can do. Next, we will dive into the two main modes of the pTx. The first mode of pTx is called static pTx, which can be represented by this figure. As demonstrated here, with the pTx system, each individual transmit channel is powered by its independent RF power amplifier, or IFPA. If we feed the same RF waveform to all the RFPAs, we can apply a channel-specific complex weight at each RFPA, which are alpha 1, alpha 2, alpha 3, and alpha 4 here. Therefore, the final waveform of each channel will be the multiplication of the RF source and the channel-specific complex weight, and we can adjust the relative amplitude and phase of the RF waveforms by adjusting the complex weight. Note that in this figure, only 4 channels are drawn, but in reality, there are oftentimes 8 channels or 16 channels or even more, but the principle is the same. For static pTx, only the channel-specific complex weights are to be determined, so the problem can be viewed as an optimization problem of the weights, given the channel-specific B1 maps and the region of interest or ROI. Based on different purposes of the static pTx shimming, we can use different objective functions. For example, to increase the homogeneity in the ROI, we can use the coefficient of variation as the loss function. And to increase the efficiency, in other words, to achieve the highest B1 amplitude within ROI, we can use mean B1 amplitude as the objective function. Or more generally, we can design a target profile and use loss function such as linear least square or magnitude least square to match the profile with the designed one. Here is a simple demo of the static pTx results. The circular polarized CP shim is the result of the default coil setting. With the homogeneity loss, with the same SAR, we may lose some B1 amplitude, but the homogeneity within the ROI will be much improved. Similarly, with efficiency loss, the efficiency, or in other words, the mean B1 amplitude will be maximized within the ROI without considering the B1 field homogeneity. The second mode of pTx is called dynamic pTx. As we mentioned before, in the pTx system, each transmit channel is driven by its independent RF PA, so we can directly feed different RF waveforms to each RF PA. In this case, the flexibility provided by the pTx system is fully exploited. In other words, the static pTx can be viewed as an extremely simplified version of dynamic pTx. But with the actual freedom provided by the dynamic pTx, we can certainly do more. Comparing to static pTx, where there are only 4 numbers to be optimized, for dynamic pTx, we need to design the RF pulses for each RF channel. One of the commonly used methods is to control the excitation K-space, which can be used to achieve various targets, such as flip angle shimming, selective excitation, and target or some target profile, etc. If you're not familiar with the term excitation K-space, I will give a more detailed introduction about it in the next slide. To understand the principle of excitation K-space, one would need some basic knowledge of the K-space. For that, I recommend you to the other video of our lab, Introduction to K-space by Chen-Yang Zhao. Basically, the K-space is the Fourier transform of the image, and the image is the inverse Fourier transform of the K-space. And so, we can control the image contrast acquired by directly controlling the K-space data through MRI sequence. The trajectory of K-space is determined by the RF pulse and the gradient. The interesting part is, this relationship between K-space and image holds true not only for acquisition, but also for excitation. That means we can obtain a desired excitation pattern by jointly designing the RF pulses and the gradients. Note that theoretically we can also use 1Tx to control the excitation K-space, but that usually leads to extremely long RF pulses that suffer from severe T2 decay. With multiple transmit channels, pTx can cover the K-space more efficiently. Therefore, it's pTx that made this application available for real problems. Now that we learned about the principle of excitation K-space, one potential application is flip angle shimming. Similar to static pTx with homogeneity loss, the purpose of flip angle shimming is also to achieve a homogeneous excitation, but it requires the dynamic pTx, and oftentimes it achieves better performance compared with static pTx. The general idea of flip angle shimming is quite simple. Since we have the knowledge of the inhomogeneous B1 field profile, we want our excitation profile, which is the inverse Fourier transform of the excitation K-space, to be nearly reciprocal to the B1 field profile, so that their multiplication is relatively uniform. And since the variation of the B1 field usually has low spatial frequency, we do not need precise control of the excitation K-space. Commonly used methods include KT points, which uses a few points in the K-space, and spokes, which uses a few lines in the K-space. Another application of dynamic pTx is selective excitation. Instead of using only a few spokes, we can use more complicated k-space trajectory to cover the excitation k-space, for example, spiral. By controlling the excitation k-space, we can selectively excite only the region we want, instead of exciting the whole slice or the whole volume. For example, in the middle here is our USC logo, and we want to use it as our target excitation profile. On the right is what we obtained. You can clearly see the SC, although the resolution is not perfect. Till now, we have covered the basic information about pTx. In summary, pTx stands for parallel RF transmission. There is static pTx mode and there is dynamic pTx mode. With static pTx, we can use it to increase B1 field efficiency or homogeneity within the ROI, or we can use it to generate a target profile. But since we can only adjust the channel weights, the improvement with static pTx is limited. With dynamic pTx, we can use it for flip angle shimming. With KT points or spokes, we can use it for selective excitation, and we can also use it to achieve a target profile. By designing different RF pulses for different channels, the performance is oftentimes better than static pTx. Okay, we've reached the end of this video. I hope now you have a better understanding of pTx and ultra-high field. If you like our video, please don't forget to follow our channel. Thank you.